So now before we go to the tutorial part, and at the end of this hour, I will talk a bit about the exercises, but now we're going to look at convolutional networks. So these are very used in mostly image processing, but also for sound, for temporal data and so on. And we're going to see first what is a convolution, how convolution layers and convolution networks work, and then some details about pooling, a bit about fully convolutional networks, although I'll talk a bit more on those next week when we look at autoencoders, and then we're going to move on to the Keras Sequential API. So from now on, we will no longer waste so much time with the TensorFlow low-level details. Those were important for you to understand how things work. But now we're going to use the Keras API, and we're going to start with the sequential model, which is the simpler one to use. And basically this changes things a bit, because now it's just a matter of knowing which kind of pieces you have to join together, and things become quite easy to use, as long as you understand how things are working underneath. So then I'll talk a bit about what we're going to do in the tutorial using fashionist, and also the optimization part that we saw in the previous lecture. So first, let's start with the convolution. This is the mathematical definition. The convolution between two functions is the integral over tau, or integral as a function with respect to tau over minus infinity to infinity, of the product of one function of tau and the other of some time displacement t minus tau. So since this is a function of tau and the other one f is as a function of tau and g as a function of minus tau, g is actually inverted and shifted with respect to f by some t value. So this integral, which is commutative, you can also do it this way, is the convolution of two functions. Of course, this is the definition, but it's not very informative because it doesn't tell us what this does and what it's used for. So I'm going to give you an example of one application of convolutions where it's easy to understand. So it's often applied to these linear time invariant systems. These are, for example, suppose that we have a bell, and when we strike the bell with a hammer, the bell starts to vibrate. And this is linear in the sense that the stronger the strike on the bell, the stronger the vibration will be, and at least within some range it will be a linear response. And it's a time invariant because the bell always responds the same way. So let's say with these oscillations, regardless of when you strike it. So if you strike it at times 0, it will be like this. If you strike it at times 1, then it will be over here. So the response doesn't depend on the time. So this would be the response function of the bell when we strike it with a hammer. Now suppose we want to know what happens to the bell if we do it if we give it two sharp strikes in sequence. So one at times 1 and one at times 1.2. What would be the response of the bell to these two sharp strikes? We can compute this by computing the convolution of the stimulus, the impulse we're giving the bell, and the response function of the bell. So this is how it would work. We take the symmetric of the response, so this is the minus t there for the response, and now we are going to compute the integral over all the tau of the product of this symmetric of the response and the impulse we give it. So this would be the idea. This is the response, this is the impulse we are giving the bell, and at this point we still did not strike the bell. Now we give it one tap and it starts oscillating, and now we give the second one, and this would be the response, the product of the two functions as we shift along tau, and this is the integral over tau of those products. So we compute the integral, and this is what happens to the integral as we move through time t. So this would be an idea of how we could apply convolution to get this product of the two functions. This is not quite what we want to do in general with convolution networks, but we can imagine that we can use convolution in a different way, which is to find a pattern. So suppose we have this strange signal we detected by radio or something like that, and we want to detect where in this signal we have that pattern of spikes. So we could use a detector function. This would be our spike detector function. And now we compute the convolution. And as we move through time, we know that the product of these two, so integrating this product over all the values, is small until we start matching the pattern. And when we match the pattern exactly, then at that time we have a very large peak in our convolution. So this way we can use convolutions to detect patterns. The patterns will be anywhere in this dimension where we are shifting, but when we find the correct pattern, we have this sharp peak there, and we know we found the pattern. Okay, so this would be for continuous convolution with the integral part. We can use discrete convolution, so instead of taking continuous values, we can take discrete steps, but it's the same thing. We're just using sums instead of the integral, but it's the same idea, those products. And in fact, we can, for a convolution neural network, we can ignore this minus infinity to infinity, because we only need to compute the convolution where we have our detector. So all these zeros over here towards infinity and the zeros towards plus infinity are irrelevant. We just need to consider this part. So in convolutional neural networks, you usually have this kernel, this set of weights here that reproduce this discrete convolution function. And we use these weights around the input with some shift by doing this multiplication. So basically we are doing a weighted average of the inputs with the kernels that we have. Formally, for the convolution, this would go from minus infinity towards infinity, but in practice we only consider the range that corresponds to our weights. So this would be a finite discrete set of values, the input for our convolution networks. For example, an image, a bitmap, or a set of frequency samples or intensity samples for a wave file or something like that. The kernel will be this finite set of parameters that we will learn. We'll train the network to identify the right patterns, and the output will be this tensor, typically with a similar size and shape as the input, which we obtain after applying all the kernels. So for 2 dimensions, we can do the same thing, but the idea is that now we are shifting in 2 dimensions. You can use the shift with the kernel, or the shift relative to the kernel, but in practice, we can imagine that the kernel is fixed and is moving relative to the input. So we can have an image, we have a small kernel, and we are scanning the image with our kernel to obtain the convolution. But this is not very important because the operation is the same, so it's just a way of understanding, of imagining what we're doing here. Another thing is that the reason why convolution is defined in this way, where we take the symmetrical of one function, is to make it commutative, and also for modeling things like those time invariant, linear time invariant systems and so on. For our purposes, it doesn't really matter if the kernel is that way or it's inverted, so we can just assume that we have our kernel, our set of weights, we are scanning through the input, and we are not inverting everything. So we don't need to use minus signs there, because in practice it will not make a difference. But formally, what we're actually doing when we are using convolution neural networks is computing cross correlations, which is equivalent to convolution minus or apart from this plus sign instead of the minus sign. But this is just a formal aspect. In practice, we just call this convolution and not cross correlation, and not worry too much if the kernel is pointing one way or the other, because it's actually learning the right weights is the only thing that matters for us in practice. So this is the idea basically of using convolution networks. We have these kernels, these sets of weights that we want the network to train in order to identify relevant patterns in our data. So let's see what we can gain by using convolutional neural networks. So one reason for this is that since the kernel is much smaller than the input, we need fewer parameters than we would need if we were to use a dense layer. So something like the multi-layer perceptron, where we need one weight, one parameter for each input value. If we have a very large image but a small kernel that is going to scan through the image, the parameters of the kernel will be a lot fewer than if we had a dense network that would receive as input the whole image. We also have this idea of shared parameters because since it's the same kernel that's going to scan through the whole input, it's actually the same weights that we're going to apply over all these windows of the input. And this makes it also that the convolution network is equivariant to some transformations. That is to say that the output of the convolution layer will change in the same way as the input when we change the input. For example, with translation. If the output of the convolution layer is the result of scanning all the input with our kernel, then if we shift our input a bit to the left, then all the values in the output corresponding to the input will be shifted a bit to the left too. So let's see with an image that makes it easier to understand. Suppose that we have a kernel that responds to edges by subtracting the intensity of some pixels by the intensity of the pixel on the left. So we can have a small kernel here that merely subtracts from each pixel the pixel on the left. And we scan through the whole image with that kernel, and we get this feature map here, where we have a larger response when the difference between the pixel and the pixel on the left is larger, and gray when it's less difference, and then a lower response when it's the opposite intensity. And you can imagine that if we shift the dog a bit to one side, then this feature map will also shift a bit to one side, but otherwise will remain the same. So this is the idea of being equivariant to the input, and we can obtain this feature map from this image with only a few parameters for the kernel that we're going to scan through the whole image. So this is the basic idea. If we use a dense network, so we have all the input here, we need for each neuron to have weights connecting to all the inputs. When we use a convolution network, then actually we are looking only at a small kernel that has a small window into the input, and it's this kernel that is going to be applied to different parts of the input. So the kernel itself has few weights. Better than that, these are shared weights, because when we apply the kernel over here, then it's the same weights as it has over here and over here. So the weights are shared between the different kernels. If we stack convolution layers, we can still get a large receptive field. So the receptive field will be the part of the input the layer can receive information from, which with a single convolution layer for the kernel is only a few pieces of the input at a time. If we had a dense layer, then each neuron will get input from all the input values. But with a convolution layer, each neuron is only getting input from a small receptive field. However, as we stack convolution layers, the neurons inside the network at deeper hidden layers will receive input from some convolution layers from a small receptive field, but this is actually covers a larger receptive field further down into the layer. So eventually, as we stack different convolution layers, the neurons from the deeper layers can actually see more of the input at the same time. So get information from more of the input at the same time. Also, since we are using the same weights for the kernel, so you can imagine that we have this neuron with these three weights that is scanning the input. So actually, when this neuron is over here, it's the same weights that we are using, and always the same weights on all of these examples, which is different from what would happen if we had a dense network and all the weights would be different and would have to be independently optimized. So one big advantage of convolutional neural networks is that it requires a lot fewer weights, parameters, than if we would to do the same thing with dense layers. Okay, so this is what we get when we apply the kernel. We scan through all the image with the same set of weights. It always responds the same way to identify some patterns and gives us the response of where these patterns occur. So in this case, it's a very simple one that looks at the difference between adjacent pixels, but it could be a more complex one for detecting other patterns. We have this equivariance of the feature map with respect to the input. So if we shift the dog a bit, the feature map also shifts. And the way this works is that we have these receptive fields. So the name comes from the inspiration of this kind of networks on the visual cortex and the retina, so our visual system. And we can apply a different number of filters. So for example, we have a black and white image here, or grayscale image here. So in this case, it would be black and white. It has only zeros and ones. You can imagine that. And you have one neuron here that has a set of weights and is looking at a receptive field that is 3 by 3. So these the small values there are the weights of the neuron, and the output on the feature map will be the inputs multiplied by the weights and added together. So this works exactly like a neuron, as we have seen. It multiplies each input by its weight, adds everything together, and then eventually has an activation function that we can add here. But we can add several features by having different neurons. All of those have their own weights towards this receptive field, and so each one can be trained to detect a different type of pattern. So one convolution layer can have multiple neurons, multiple filters that are being applied to the input, and so learn to identify different patterns in the input. Generally, we can represent the result of these convolution layers in 3 dimensions, because we have this 2-dimensional input. Note that I'm assuming that we are using this for data like images, which is the most common case for convolution networks and the kind of examples we're going to see. So it's easier to imagine here. But you could also use 1D convolution for example, time series, sound, something like that. But we're going to draw these representations as if it was images that we were dealing with. So you have the initial image here, and we can represent here the set of neurons or the result of the convolution, which is the feature maps that we're going to obtain by applying each neuron in the convolution layer to the whole image. So basically, we have this width and height here of the feature map, which will be determined by the input and by how we are moving the receptive field here. Note that the image in this case has 5 by 5 inputs, but since we are keeping this window of 3 by 3 always inside the input, the feature map is only 3 by 3 too, because we cannot shift more and would be left outside of the input. So this height and width will depend on how we scan through the input with our neurons. And the depth is the number of feature maps that we will produce, so the number of filters that we are using, each one consisting of a different neuron with different parameters. So basically, our convolution layers can be composed of a stack of different neurons, each one with its own parameters, and that then is being used to scan through the input and produce these feature maps. So then we can do a nonlinear transformation because the convolution operation here is a linear transformation. We are just summing up the weighted values of the inputs multiplied by the weights of each neuron. So for each neuron we have a linear combination of the inputs, but now we can apply some activation function, for example rectified linear unit, and do a nonlinear transformation before we pass on to the next convolution layer. To parameterize the convolution layer, we need to decide on a few things. First, the depth of the layer. The depth of the layer is the number of neurons we're going to put into the layer, each one computing a different feature map. Note that if we are stacking these layers, then suppose, for example, this layer already has a depth of 3, so we have 3 feature maps here. This means that each neuron will have weights to all the 3 different feature maps on the previous layer. So in general, this is how it works. As we increase the depth of our layers, we also increase the number of parameters in the next layer, because each neuron will receive inputs over all the different filters that we are using. So this is one thing that we need to determine, how deep each layer is, how many filters it has, because this determines how many feature maps it will generate for the next layer. Then we need to determine the stride. This is how much the receptive field jumps when we are scanning through the image. Here, for example, you see a stride of 1. We are stepping 1 pixel at a time as we scan through the image. Here you can see a stride of 2. We advance by 2 pixels, so we advance faster. You can have, for example, a stride equal to the size of the kernel. This means that it will never overlap and you change from one side to the other, or you can have whatever stride you want. So this is a hyperparameter that you need to decide about your convolution layer. And just to recall, these hyperparameters are basically those parameters we can change, but they are not learned automatically by the model. So you set the stride and that is fixed for your network. It's part of the specification of the network. Another thing that we can use is padding to prevent the output from shrinking. So for example, here there is no padding. It means that we scan the image with our kernel and we stop when we reach the edge of the image. This means that the output will then be smaller than the input, because there are some positions we cannot reach because our kernel would step out partially outside the image. We can prevent this by adding this padding, this outer edge of the image, so that our kernel can scan through the whole image, and the feature map that results from this scan has the same size as the input. So we can do this, we can use padding by putting, for example, zeros, or by copying the closest values, something like that. So in this case, the padding is done with zeros, but there are other options for this. So these are the kinds of hyperparameters you can fine-tune, you can choose when you are creating a convolution network to determine how each layer behaves. For example, here you have an example of a convolution network that uses these different convolution layers with rectified linear units, and then pooling and so on. And at each layer, the kernels are responding to different patterns. And this is how the network then learns, by adjusting those patterns, learns to classify the different images. So we already saw these activations. This is just applying the rectified linear unit to the feature maps output by the convolution layers. We saw the convolution layers. They can have several filters, so they can produce several feature maps at each layer. But now we're going to see this pooling part. So typically, a convolution layer has these convolutions, and then some non-linear activation, but you can also stack them with pooling operations that aggregate the outputs for different regions into single outputs. So typically, the architecture of a convolutional network has these layers alternating in a way that is optimized for each particular problem. So the idea of pooling is to aggregate outputs from regions into single values. For example, this would be an example of max pooling with a stride of 2 and a size of 2 by 2. So what we get is for this part of the input, that can be a feature map, for example, from a previous convolution layer, we get the maximum value of these 4 cells, and this is the 6 there. Then we step with a stride of 2 into this region, we get the maximum of this one, and that's the 8, the 3 here, and the 4. So we are reducing the size of the input by taking the maximum value over each region. This has some advantages, which are to basically reduce the dimension of the input, and also if we add a stride to pooling, and if the stride is equal to the size of these regions, then we can actually do this kind of pooling without overlaps. So for example, if we are doing pooling 2 by 2 with a stride of 2, then there is no overlap between the two regions. So what we want to do this for is basically so that we can reduce the size of the input, sometimes this is useful, and also to make the model less sensitive to small shifts in input. So suppose that everything was shifted a bit here to the left, we would still get this 6 here, we would get this 8 here, and the after pooling, the value would still be the same. So there would be some small differences, but they would be slight because you would still find the value somewhere inside the region. So this is two things that pooling can do. With stride, you can reduce the dimension, and you can aggregate values and make your network less sensitive to small shifts in the position of some values in the input. You can do pooling with max pooling by taking the maximum value, by taking the average, by taking the mean root square of the values. There are different ways of doing pooling, but the idea is the same. Making your network less sensitive to small shifts in input, and often by using the stride of the pooling to reduce the size of the input that is given to the next layer. We can also do a fully convolution network. So typically when we are doing convolution networks for classification, what we have is a set of convolution layers and pooling and all those things, but then eventually we put a few dense layers at the end so that we have the classifier. So this is typically what is done when we want some classification. For example, we have an image input here, and then we want to know if it's a cat, a dog, a boat, something like that. This has a drawback that it forces the input to have a fixed size, because even though the feature maps we generate will just be a function of the input size, because we are scanning with the kernel, and if we had a larger image we would just have a larger feature map here, that would be no problem. But then when we reach the dense layers, we have a fixed number of neurons with a fixed number of inputs, so we cannot have different sizes of image feeding into the same network for this kind of purpose when we have this architecture. We need to do some rescaling or padding or something like that so that the inputs are always the same size. But if we have a fully convolution network, this doesn't happen, because we have an input here of some size. This will determine the size of the feature maps here. We can increase the number of filters, do pooling to decrease the size and so on. But as long as the image is not too small that this goes down to 0, we can also then invert the pooling, so do oversampling here in some way. We're going to look at this a bit more in the next week. And then by using full always convolution layers, in this case, what we get at the end is, for example, a segmentation mask where we are identifying different elements of the image. But this mask, the size of this mask, will depend on the size of the input. So if we have a larger image, we just have a larger mask on the output. So with a fully convolution network, the dimensions will just be proportional, and we keep the spatial relations between the final map and the original image, which is something that doesn't happen when we add these dense layers and then we lose all these spatial relations. So it's also possible to use fully convolution networks, and this is done with this kind of semantic segmentation where we want not to classify the whole image, but determine which part of the image is the rabbit, which part is the cat, and that kind of problem. Okay, so now let's move on to a slightly lighter subject, which is how to build this kind of models with the Keras interface. So what you need to do is to import a set of classes that you're going to use, or you just import Keras if you want to the different modules for Keras. But basically, in the optimizers module, you have the optimizers. We can use stochastic gradient descent, but you can experiment with the others I referred to in the previous lecture. This would be just an example. Then we need the model itself. So from the model, we're going to import the sequential class. This is the sequential model that we're going to use to stack different layers. And now we need to import from the layers module the different layers that we're going to use. So we have activations. We have this flatten to convert two-dimensional data into one-dimensional to input into the dense layers, a dropout layer for regularization. The dense layer is the one we've been using for multi-layer perceptrons. The convolution 2D layer is this kind of convolution layers we've been talking about. The max pooling 2D does max pooling in 2 dimensions, and then we can also add batch normalization layers. So basically, as long as you understand what these things do, it's very easy to use, because you just look at the documentation and see what are the classes that you need for the different layers. You import those, and then you just add them together. So we can create a sequential model with nothing inside. We can also give a list of the layers we want, but this is one way of doing it. You create a sequential model, and then you add in sequence what kind of things you want. For the first layer that you add, you need to specify the input shape. So in this case, we're going to look at the fashion MNIST. I think I have a picture here. So this is similar to the one you used last week for the handwritten digits, the MNIST dataset. But this one is a bit harder for the neural networks, and it's built of small images of clothes. So you have trousers and t-shirts and things like that. And you want to train, it also has 10 classes. The dimensions is the same as MNIST, so it works on the same networks you were using for MNIST. But it's a bit more difficult because MNIST is really simple for the network to learn. So we're going to use this one, and we're going to stack up these layers by starting with the convolution layer that has kernels with this shape, 3 by 3. It will have 32 filters, so this convolution layer uses 32 neurons which look at fields of 3 by 3. So each neuron has 9 weights, and it's scanning through the image. The output of this convolution layer will be 32 feature maps, each one produced by one of the 32 neurons. We can use this same padding. It means that we are adding this border to our image so that we can keep the same size on the output. And we must give for the first layer in our model, we must tell it what is the shape of the input. So in this case, we have an input of 28 by 28 pixels and one single channel. By default, the Keras uses this convention, which is the size of the input, 28 by 28, and the number of channels. If you use, for example, color images, you would have a 3 here because you have the red, green, and blue. Note that in the input shape, we are not saying how many examples there will be. So that actually the convolution layer will receive 4-dimensional tensors, which has on the first dimension the number of examples in the mini batch, and then the size of the image, the number of color channels, and so forth. So this is the convolution layer. Then we add an activation, a rectified linear unit activation, Then we can add a few more layers. So I'm going to specify this in the exercise. But then you can put pooling layers by telling the size of the pooling and using max pooling. Dropout layers. This is the probability of ignoring some inputs and so forth. So dropout is not often used in convolution layers. It's more used when you have dense layers, but you can also experiment here. I took this from a tutorial where they used dropout in convolution layers, so you can experiment with and without dropout in the convolution layers in the tutorial. So then at the end of the convolution part of the network, we need to feed the output of the convolution parts here. So we finish the convolution and we need to feed this into the dense layer for the classification. So since the feature maps on the convolution layer have these two dimensions, we are going to flatten everything before feeding into the dense layers. So we add this flatten layer, and then we add the dense layer with 512 neurons, another one with 10, with dropout, and so forth. Note that we had to give the shape of the input at the beginning of the model, but for all the other layers we don't need to do that, because Keras will automatically compute what is the size of the input for each layer. So this makes it a lot easier to build our complex models, because we don't need to worry about how to compute all these sizes and implement all the layers. So when we do this, we have the complete model here. We create an optimizer, for example, stochastic gradient descent with some initial learning rate, 0.9 momentum, and now we can also add the decay value for here. So this is one of those parameters I talked about. You can tell the optimizer to gradually reduce the learning rate by some value. So in this case, the decay is the initial learning rate divided by the number of epochs that we want to do, so that the learning rate will start to decrease gradually by this fraction every epoch. Now we call our function to create a model. So this would be the create model function, which created all the model. I just presented part of it here, but we can just call the function we wrote that does all this, creates the model, and then we need to compile the model. So when we call compile, Keras will take care of creating all the computation graph, and so it needs to know what is the loss function that we want. So in this case, we want categorical cross entropy because we're trying to predict the different classes here. And so we have this softmax activation on our dense network. Note that Keras automatically takes care of those problems of using the logits for the loss function and so on. So we don't need to worry about those details, but it's important that you remember that there are some numerical stability issues that are being solved here. We also can say what kind of metric we want to be recorded, and we can use this accuracy. And now we're going to train with our model. So we have the features, which are those images that we're going to feed into the model. We have the labels, the class labels here, and we can use part of the data for training and leave out part of the data for validation here. So it's something that is left out that we're going to use to track the training. We can specify the size of the batch, the number of epochs, and then at the end we can save the weights of our trained model. So we start seeing the training results and we save everything at the end. These weights then can be loaded, so we can create the model, compile it, and load the weights by just using the same file name. And so we can use the model after training and reuse it with the same weights. If you want, you can check the model. You can use this summary methods, and it will print out the architecture of the model, the number of parameters, and so on. And you can also use these callbacks from Keras. For example, the TensorBoard callback. You can specify a folder for your logs. You can add this argument to write the computation graph too. And then you can add callbacks when you're training your model. So when you call the fit method, you can add a list of callbacks here that will be executed, that have some functionality that will be executed during training. So this is a way, for example, to keep an update of how your training is going into the TensorBoard logs, and you can turn on TensorBoard and follow your training in this way. There are also other reasons for using callbacks. You can use callbacks to save checkpoints of your model. So if you're afraid that the electricity will fail or something like that, or the computer crash or something like that, so you can save regular checkpoints for your model. You can monitor the learning rate, the validation error. There are many different possibilities, and you can even write your own callbacks. So we're not going to delve too deeply into these details, but Keras is quite flexible. At the level we're going to look at over today is just building these basic models. Next week we're going to see the functional model and look a bit more about how we can subclass these some of these different layers and models. But we're not going to go into much detail here. You can explore that part on your own afterwards if you want to, but there is a lot of flexibility in this case. The basic idea is that we need callbacks because we are calling the fit method, and Keras is taking care of all the training. So since we don't have that training loop that we were building when we used raw TensorFlow, we need to have some way of being called back from inside the loop in order to do something that we want, saving results, visualizing data, or changing anything. So you can take a look here at the Keras documentation for more callbacks if you want to. The fit method also returns an object, this history object, that gives you the values for all the epochs of whatever metrics you want here. So in this case we're using accuracy, and it also includes loss and validation, accuracy and loss. And so you have the result, the vectors for these measures over all the epochs if you want to plot them anyway in this history attribute of the history object. Actually, this history object also has other informations, but this is usually the most useful one that we can use, because this way you can also do your own plots of how the training went. Okay, so our tutorial will be to use fashionist, part of the tutorial, to train your network to classify these images into the 10 classes of clothing. Basically, you're going to do something similar to what we did last week. You're going to use these data sets from Keras and download fashionist. So the first time you do this load data, it will figure out that you don't have the data set in your computer. It will download it and give you the data. From then on, every time you use it, will use the data cached in your computer, so you don't need to download anymore. Then we're going to reshape the training data, because each image is stored as a set of 700 and something pixels in a single row in the data set. We're going to reshape that into 28 by 28 images, convert it to float 32, and then we're going to use this two categorical function here to give us the one-hot encoding of the classes that we need to compare with the prediction, the softmax prediction, because the labels that come here are just integers from 0 to 9, and what we need is that one-hot encoding that we saw last week. Okay, so this is basically setting up the data set. Then we're going to do implement this network with the Keras sequential model, and you can look up the documentation to see what these things mean. So the kind of padding, the activation, the batch normalization, and the size of the kernel. You're going to do these layers like this, then max pooling, 2 more convolution layers, then the dense layer with 512 neurons, and then the softmax layer with 10 neurons and use this stochastic gradient descent optimizer. So this is the basic, the vanilla thing, and I just want you to save this after fitting, because next week we're going to look at transfer learning, and you're going to use this pre-trained network to help classify the MNIST dataset. So transferring what the network learned on this dataset into a new dataset. But apart from this, so before we go into the summary, I also want to take a look at the other exercises. So this one, the 8.4, is the one where you implement the convolutional neural network for the fashionist. But before that, just to get some practice with the Keras model and experiment a bit, I would like you to reuse the data for the miles per gallon example from last week. But now you're going to write your models using the sequential model of Keras, which makes it easier to experiment with different architectures and also experiment a bit with different optimizers, learning rates, and so on. This is not a very serious thing, so it's not the objective is not for you to actually improve the result, but I would like you to get a feeling of what happens if you use a learning rate that is too large, what happens with different optimizers, when you have a larger network or smaller network, and so on. So this is a simple example just for you to play around a bit with Keras and get a feeling for the results. So if you want, you can use TensorBoard. If you don't want, I usually don't use TensorBoard when I'm doing something quickly. One alternative is just to after training, you look at the history object that you have. So the fit method gives you this object. You just go into the history attribute there and you plot the training values and the training accuracy and the test and or the mean squared error in this case. So you shouldn't use accuracy for regression problems, but you can compute the mean squared error and take a look at that. So basically, try to get a feeling for what can go wrong or right when you adjust these parameters. And after you've done this for a bit, you can move on to the fashionist and the convolution network. So this is all for this part. Just to wrap things up, we saw what convolutions are and why we want to use them in convolution networks. So basically, we're trying to train these kernels, these neurons, to identify specific patterns. And then we stack up lots of them into a large network so that we can identify patterns and patterns of patterns and so on. We also saw this API for Keras, which is what we're going to start using from now on. So today we're going to use the sequential model, which is very simple and easy to use, but is not very flexible if you want to do more tricky things. Next week we are going to look at the functional model. So if you want to, I recommend that you read chapter 9 of the textbook, which is about convolution networks. And now let's take a 10-minute break and we'll meet at the Hangout at say 6:15. Okay, so see you in a bit.